that we're somewhere in the middle of that first problem. We didn't get very far. That's what I had down. I don't remember if I was writing this down after you stopped paying attention or what. But let's go to finding the area under this curve with 1,000 rectangles. 1,000. Now, with 1,000 rectangles, this amount of error here would get minimized. When I have, you don't need to necessarily draw this, but if I were to do a visual here, if I did 2 rectangles, this red, that would be my error. Okay? If I did 4 rectangles, this blue, that would be my error. Now look at how much error I lose by using 4. This now, that's not error anymore by going to 4. I get a lot less error by going from 2 rectangles down to 4. I almost took my error by half. If I continue to do that, then, for example, 8 rectangles, imagine how much then I would lose there. I would lose a lot of that blue section right here and so on. Okay? The name of the game then is more accuracy with more rectangles. Now then, here we go. We are going to write in summation notation a formula for the area if I used 1,000 rectangles. Let's start with the base, delta x. Delta x comes from the total region divided by how many chunks? What's the total region? 3. Is it 3? Why is it 3? Oh, because I didn't actually, we didn't actually go over here, did we? Okay, sorry, no wonder. Okay, so the region is from 1 to 4, so it's 3 wide. Now if I divide 3 wide into 1,000 chunks, then each chunk is 3 1,000ths wide. That 3 1,000ths there stands for what, rectangle-wise? Base of each rectangle. It's very, very thin. If I were to draw this, it would actually be pretty much a pen wide. All right, times the height. The height is f at the components that go into, here's where my x is, or here. Well, that mark depends on where I started. Where did I start in this problem? 1. And how many deltas I've gone over. Well, delta is every time 3 over 1,000, and how many deltas over is a counter. 1 delta over, 2 deltas over, 3 deltas over. We call that pi. I starts at 1 delta over because we're using right rectangles, and it ends at the total number of deltas over, and the total number of deltas is the same as the number of rectangles, which is 1,000. All right. Pick up your calculator, please. First thing you're going to want to do is get the function in there. So I typically would go here, and I think it's x squared plus 1. Am I correct? Okay. The graph for that is fine. We kind of know that graph doesn't help us much. It's really just putting the function. You with me so far? Okay, here's where it gets a little wacky. So follow along carefully, and I'll try and go slow. Go back to your scratch pad. We're going to create. Now, I could type in the summation, like, yes, sir? Oh, is it? Oh, thanks for telling me. Now, better late than never. A little late, but not too late. Thank you, Esther. I guess my obvious question would be, then I said, the function is x squared plus 1, right? And I distinctly heard a couple, Why? Oh my goodness. Okay, so we're going to create a function now. My goal would be to create a general function, not just this specific calculation. Now I could type this in, and it would give me 1,000, and then just keep typing over with changes. In fact, in the interest of time, let's actually do that. So we're going to just type this in as we see it. The summation, the best place to go is right here. right next to the 9, the catalog subfunction on the Inspire. If you have an 84, I believe it's math 0 or summation. I'm not sure about that. It's right here is the summation button. Look next to it, by the way, just to improve your math knowledge. This Greek S, that Greek pi. Greek S adds many things over and over. What do you think Greek pi does? Stands for product. Yeah, it multiplies many things over and over in the product. But we don't use it much. It's not very useful. So, pick the summation button. Okay? Now, type it in just as you see it. The calculator is beautiful. I equals 1 is our starting value. 1,000 is our next value. In the function, I first need to type in 3 divided by 1,000. I guess you could also use decimals. Divided by 1, 1, 2, 3. I need, don't I want 2 sets of parentheses? Okay, and then our function. Our function has been identified, so I can type in and 1 plus, I'll just go 0.003, and then times I. That then is bad, because I get an error. Why did I get an error? Oh, I have 2 division signs there, that's right. Okay, I get 24.0225. How about you? Yes? Yes? No? Okay. Okay, would you then tell me what it would equal with 10,000 rectangles, please? 10,000 rectangles. Recalculate with 10,000 rectangles. 21.022? What did I get? Why? Did I do something wrong? Oh, shoot. So is everybody getting 22-ish? Oh, I did not. Sorry, enter. Sorry, I still have my +1 in there. 21.0225? Yes. Okay, sorry, I didn't hear it. Okay, 21.0225. Did you recalculate with 10,000 rectangles? Okay, did you recalculate with 10,000 rectangles? All right, I assume that's yes. So, now, rather than retype, we could create a function that could be used to estimate for any number of rectangles. So let's create a function. I'm going to call it A sub n for area as a function of number of rectangles. All right? Now, generally speaking then, if n rectangles, what's the base of each? Based on any number of rectangles, what's the base? 3 over n. 3 divided by however many rectangles you want. Times the heights. The heights are f at the starting value plus delta x is over. So the function at what x's? 1 plus delta x. What's delta x? 3 over n. How many times? I times. From I equal 1 to I equal n. Some number of rectangles. Now, to create such a function, I typically create functions in the graphing menu, but this doesn't go well in graphing menu when it's a function of n, not x. So instead, I want you to see how to create a function. If you don't already know, I don't know if maybe you already know this. But this guy right here, that little blue colon with an equal, that's super useful in Calc 2 especially, all right? We want to create a function. I'm going to call it a sub n. Actually, maybe it would do better to, let's see how a sub goes. A, parentheses, n. Okay, now you're going to say, let this be defined as. That's what this button is for. Control that gives you a colon equal. Let that be defined as. This function here we just wrote. So, summation from I equal 1, I equal 1 to n of parentheses 3 divided by n, new parentheses, oops, darn it, new parentheses, f, the function we define at 1 plus 3 divided by n times I. Okay, it says cool. I define that function. Are you with me? Now, if I wanted to estimate based on any number of rectangles, I could just go to vars, and now I have a function named A. I could choose it and say, all right, 1,000 rectangles. Oh no, that's bad. I think the calculator doesn't like A, quite frankly. Let's go back here and I'll do it the way I would normally do it. I was hoping A would work, but it didn't. Oh, darn it. Would you scroll back over here?
It showed us when I can check it.
It showed what? You got an answer?
Yeah.
How come I didn't get an answer?
Oh, I don't know.
Oh. Maybe mine's bad.
You put the I on the bottom.
Yeah. Maybe I don't see why that would be an issue unless I had a 1 in the denominator, which I didn't. Let's go with that. Times I, is that what you did? Okay, so let me try again and see if my function works now for 1,000. Glad yours worked. Okay. Now, that's great as an approximation, 21.022. If you then did the function with 10,000, don't get crazy because then the calculator will get locked in a loop. But 21.00222. Now, it seems like the answer is converging on a final answer of 21. Now, it'll make you happy to hear that with calculus you could do this in a fourth of the time exactly, but we are not there yet. So, let's go back to then the notes. I think we'll practice with the calculator. Let's go to this part. Am I in the right place? The next part is write or recognize summation notation with a specific function. Is this right? This is not what you have in your notes, is it?
Well, it's on the back.
So I'm missing a slide, I think. Or maybe it's down here. Nope. Sorry, give me 1 second while I paste that slide in. I do want it, I'm sure. Apologize. Okay, so would you try expressing that area under that curve using sigma notation? Then create a function that would estimate this for n of 7, 28, 100, and 1,000. Go, go, go. Yeah. You do not need to drive. So is your delta x 3 over n this time? Oh, Mr. Ingram, your answer, your delta x is not 3 over n because delta is not 3, it's 7. The region is 7 wide, not 3 wide. Remember, you're going to have to change the function. It's not the same. Yes. I equals is not the starting x value, it's the number of rectangles you've gone over, and you always start by going one rectangle over. The 3 shows up here, but it would always be one rectangle over, 2 rectangles over, so I right always start with numbers. Yes, it says, sorry, it says at the top of the page, always right, always each. Today, not always ever, forever, just always today. Seven. Check your work, and I'm getting for A of 7, 183.644. How about you? Yes? No, that's not what you got?
It's the total range over. I was confusing that.
Okay.
Oh, you said I. You said I.
Yes. I starts at 1. Okay. Remember, does not signify the starting region. I is how many rectangles you've gone over, and you always go 1 over. If we're using right, we always are going to start at 1 rectangle over, 2 rectangles over. So I is the rectangle count. It's not the starting x value. Anybody confirm that 183.644 result? Yes. Cool. Right on. Okay, minute 28. 28, 147.716. I assume that's more precision. 100. The 100 rectangles, 172.570. That's 1,000 rectangles. Oh, shoot, I just spent these to be valued. Okay. Yes.
Doesn't the function start on 3 or 1?
It does. So are you having a problem with this?
Yeah.
Now that is not the starting value of the region. It's the starting value of how many rectangles. I represents rectangles. And we're starting with one rectangle over, two rectangles over, three rectangles. Yeah. The three, that's represented there. And that's the one we built. Yeah. Okay, so 171.819. Yes, on right-hand rectangles it will always be one. I will always be one. All right, so it looks like we're getting closer and closer to the 171-ish region. Are we good? Okay, let's go to looking at this at a little different. We're going to blow off the calculator part of this. It seems like that's going okay. So for the following, write the summation notation. So the area function here with n equal 5 would be, let's start with delta x. What's delta x for this first one? The total region is 5 divided by n, which is 5. So the region or the base of each rectangle is 1 times the heights, which are f at. What goes into the f at is the starting value plus how many deltas? So f at what? 1 plus each delta is 1. How many times? I times. From I equal 1 to I equal, in this case, 5. All right? How about second one? The amount, the area as a function of 6 rectangles would be summation. Each base is a half. Total region of 3 divided by 6 chunks. Each base is a half. Each height is f at the starting value. 0 plus how many deltas over? Well, each delta is a half, and how many over? I times. Starting from an I of 1 and going to an I of 6. Okay? You do the next two, and then we'll talk about going backwards. You tend to go too fast sometimes, so please tell me if you need to slow down. One is entirely. Is that about what you have? Okay. Now, these are just little nibbles at a time, gradually, progressively getting harder. Let's say we went backwards. So I'm giving you the summation. I want you to tell me what's the region and what's the number of rectangles. So for the first one, the region, there actually are two calculations that go into the region. Where does it start and how wide is the total region? Now, how should the starting point's the easiest place to find. Where do I look for the starting of the region? Right there. That tells you the start. Find the start of the region first. Okay? I know that the region starts at 1. Okay? This tells me, well, kind of tells me, a little tells me. Does that mean the region is too wide? Oh, it doesn't. Doggone it. What goes into that calculation is the total region divided by n. And so we should probably find, actually, I said that's my next thing, but I'm going to find n next. N is 12. 12 rectangles. Now, if each base was 2 wide, and there were 12 of them, the total region was, let me go back here, okay? This represents each little delta x is 2, right? Now, each delta is 2, and there were times 12 deltas, so the total region is how wide? 24 wide. Well, if it starts at 1 and it's 24 wide, it goes to 25. Okay, with an n of 12. Let's do another one together. What's the starting value? -1. What's the number of rectangles? 4. If I take 4 rectangles, each 1/2 wide, 4 rectangles, each 1/2 wide, the total width is 2. Now if I start at -1, go 2 wide, the other end point is 1. Okay? That total region is the hardest part. The total region is a single delta x times the number of rectangles each time. All right, and what else was I supposed to say? What's n again? 4. All right, do the others, please. Tell me the region and tell me the number of rectangles. Did you get 0 to 3 for the next one? And the last one? 4 to what? 9. 4 to 9 with an n of 10, right? Okay. All right. I think we're on the back now. Is this true? Okay. Now sometimes, rather than f in the problem, you'll actually see a function, and that's where things start to get a little hairy. Write an expression involving signal without the f for rem. That's the first time I think I've used that abbreviation. That's right rectangle approximation method. It is not a notation you'll see on the AP test, but it is a notation you'll see in many textbooks, not ours. Okay, right rectangle approximation method. RRAM is right, left LRAM is left, MRAM. You'll see, I don't see a lot of URAM or they definitely don't use LRAM for lower. If you see LRAM, it's left, not lower. Okay, so let's go here. Let's start with doing it the way we were doing it, which is to say the area as a function of, this time generic in rectangles, is, what's delta x here, please? 3 over what? N in this case. 3 region-wide divided into some indeterminate number of rectangles. Times f at 1 plus 3 over n, how many times? I times. starting from 1 to n. All right, now what I'm talking about in this problem then is rewrite it now with the specific function. So I'm saying call this something more like 3 over n is fine, but instead of f at, I'm going to say this function is 3 plus 2 blank squared. So 3 plus 2 blank squared. And what's the x? Well, this is the x for each function. And so that is what, there's my pencil. That's what goes there. Now, it's pretty common then on the AP test, then they're going to ask you, say, based on this, what's the region and what's the function? You need to kind of figure out, wade through it all. It's pretty rough, but you'll get there. So, would you look backwards at this, for example? This involves going backwards. So, this is like a rectangle problem, but instead of an f, this is a specific function being given. So let's start with the easy parts. What do you reckon the region is? What does it feel like the starting point is of the region? 2. I agree. Okay. What is the number of rectangles? Oh, never mind. What's the total width of the region? Total width of the region is? 4. Okay, remember each subdivision is the total region divided by how many rectangles? 4 over n means the total region is 4. And they divided it in chunks, so it's 4 wide. Well, if it started at 2, went 4 wide, it ends at 6. Okay, last but not least, it seems like that x value of start plus delta x is over is being squared. So therefore the function must be just straight up x squared. Okay, I don't actually even know what it was called after. It might be g for all I, you know. Are you following? I think there's some little practice problems underneath that for you. Is that correct? Okay, you can come back and do those later. Let's go back to the last set of examples. This is the last skill you're going to need to succeed on tomorrow's lesson, which is a humdinger. Make sure you get a good breakfast tomorrow, because tomorrow's lesson is a humdinger. Some functions can be broken up into several functions added. Now, first of all, I'm talking general math here. Can you break up integral into separate integrals? Is that okay? Is that a yes? Yes, you can do that. The sum in an integral can be broken into separate sums. Okay? The derivative, for example, of a sum is equal to the separate derivatives. That's a yes. Some, however, cannot. For example, if you square root a sum, is it equal to the sum of the square roots? It is not. That is not allowed. So my point then is in math, sometimes when you have a sum in a function, sometimes you can split it, and sometimes you cannot. Well, what about sigma notation? Can I split this up into lots of little functions? Feels like yes or feels like no? Okay, not sure, and you're right to not be sure. So let's develop it, shall we? Do you agree that when you do a summation, this is like a lot of function evaluation problems? For example, when I equals 1, you would have 4 plus 5 times 1 plus 6 times 1 squared. Then you'd put in I equal 2, and you'd have 4 plus 5 times 2 plus 6 times 2 squared. And then you'd do I equal 3, and then I equal whatever, until you got to the last number in I equal n. And when you put in and you'd get 4 plus 5 times n plus 6 times n squared. Isn't that what summation means? Put I equal 1 in, through the last value in, and add up all the quantities. You with me? All right, now the point is then that, can I break this up? Well, it's all addition, and addition is commutative. And so, why couldn't I say, well, look at all those 4s. I could bust that up into, actually, I'm not going to go there, I'm going to go a little slower. I could group all those 4s together, 4 plus 4 plus, and put those in a set of parentheses. Likewise, I could find all those 5s. And in fact, all those 5s would have a common factor of 5 out, and I could just say what's 1 plus 2 plus da 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 plus n. And then I could say, look at all those terms with the 6. I could rearrange it so all those together. And I could put a 6 out front. And inside, I'd have 1 squared plus 2 squared plus 3 squared through n squared, yeah? Therefore, that big old one-term sum could be written as 3 different functions, the sum of a bunch of 4s, from the first time I got a 4 through the last time I got a 4. Plus, there's no reason I would need the 5 in the summation. I could write the 5 out front of the sum of a bunch of just plain old numbers. 1, 2, 3, that's basically just I, counting up from 1 to n. Plus, this is like a 6 out front times the sum of a bunch of squares put in. Now that's a skill to take from here down to here. We need to have for tomorrow to go well. It's not too hard, it's just a little bit of algebra. And so I think I have not time for quotient rule. So let me do an example. So for example, number 9. This is what I'm looking for you to do. Okay? First, I want to simplify this. Did I have an, oh, sorry, that's this tab right there. First, I want to break this up. This 2 over n, I know it feels like a variable expression, but it's not an I expression. So this is actually a greatest common factor. It can be brought out front. And that I is inside the parentheses. You with me? Likewise, this sum can be broken up into 2 separate sums. 2 over n times the sum of a bunch of 2's, and 2 over n times this guy. Now again, once I get to this separate sum, the 2 over n is the greatest common factor. It can be brought out, and I just need to add all the I terms. This is what I want you to be able to do, is to blow up a one-term expression into lots of little terms. That's what I'm looking for on 9, A, B, and C. That's your final answer. It's not hard. It's really just separating the terms of a sum and pulling any n terms out front, and any constant or I terms stay inside. Okay? Because you have to sum them. All right, that should be good on the homework for tonight. Now, Then you'd have probably a couple little problems here and there to do, yes? This is set 42. I haven't taught set 42 yet, and I'm not going to have time, at least not to do it well. I could do a really terrible job in 3 minutes, but it wouldn't help much. This is not due tomorrow, but if I were you, I would get a little bit of it started, maybe 10 to 15 problems that gets done tonight, and you'll be glad you did. Obviously, you should not do the ones that you do not know how to do on set 42 closure rule, unless you have the training for it. What's the mnemonic? Low D, I minus I below. Okay. Do you still have set 41? Okay. Tell me what questions you might have on 41, and I'll either do them up here or put them on a key online so I can get 41 today. I don't want to be too backed up. 41 questions. 3.
No, wait, no.
Not 3. 4, 7. Right here, 9. 4, 7, 9. 8. 12.
I think, I don't know.
10. 4, 7, 8, 9, 10, and 12. Is that it? Not that that's not enough. Yes.
I did all of those already, God.
All right. I will put a key with these problems online at lunch. This time I'll remember. And those will be there. Set 42 is not, let's make this 100% clear. 41 is due today. The fun sheet 43 is due tomorrow. You should start set 42 tonight, but it is due Wednesday. And that's good. Basic will be
Minus 9.
glad to hear.
Good morning, Devlin Jaguars. Please rise to the Pledge of Allegiance.
All over the desk.
Please begin. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
I'm literally like, yeah.
Callahan Foster. Cal is a great student that is always ready to learn as he walks through the door. During class, he's always asking questions that help him get easier to understand the complex concepts of the world. His enthusiasm and determination to learn concepts enhances the learning for everyone in the classroom.
Julia's excitement for learning is exemplary in education. She's shown an uncommon dedication to working through our inquiry-based labs in 80 cities and is a creative problem solver. She has also been an incredibly dedicated anchor member of the Dental Service Corps. She has proven herself to be an invaluable part of all of our projects over the past 2 years, and her commitment to service for the sake of serving the deaf.
And Brady Sullivan. Brady is not afraid to approach all types of challenges with boldness. He seems to thrive and even derive joy from untangling difficult questions and will not stop working on a problem until it gets tackled. He has come in many times outside of class for clarification or to explore a topic more in detail. I've really appreciated his follow through and enthusiasm for the content. He's a leader to his peers by his positive presence in the classroom.
Today, the University of Northern Colorado from Greeley will be counseling during 7th hour. We have 7
first time that there was
Sailors from Waco, Texas, visited Tuesday, October 19th during September. One of our passengers discovered a little
Hey Jack, we're here for that one got talent. Talent show is on Thursday, October 18th at 7 o'clock. And auditions are after 2:45 on October 10th. Sign up to our outside
Bring two number 2 pencils, no mechanical, adaptive extra battery, under extended neck. Do not bring your smartwatch or cell phone. Cell phones, smartwatches are not allowed in the cemetery.
10th graders last day state for Coco report to the counseling office for 7th hour, and last named Albert F. will report to 100. Tomorrow, last named Conway to Garcia will request counseling, and Nathan Group, who will report to E100.
An enormous congratulations to the marching band for 2 amazing performances at the Flagship Marching Festival. The band got first place not only in 3A, but first place in the entire competition. 3 more weeks of hard work and dedication.
Good job, Ben.
Emily Belmonte competed for Green Mountain High School University only invitational this past Saturday and placed third on bars with her highest score of the season. Congrats, Emily.
Yeah, tonight riding for Chatfield Mountain Biking Team. Won the JV category at the Haymaker Classic High School race in Eagle, Colorado this Saturday. And Mia scored first place finish, making her the JV Girls Division champion. Mia will be racing for the overall state champion title on October 20th in Durango, Colorado.
Congratulations to the DHS cross country team for another incredible meet. Eliana Thompson and Taylor Harris led the girls, again moving them up their all-time course. Taylor Fadings led the boys and conquered a long-time goal. These exciting races were accompanied by great performances and PRs for the majority of the team. We are so proud of our runners. Good luck at league championship on Thursday. That's all your message. Have a great day.
Have a good day, people.